C.2, 3-element partition. In the introduction video, I explained the partition idea. Here, we take a special partition way. It's called a 3-element partition. There is a pretty smart trick used here. Yeah. But we need to do a lot of work. Yeah. But this 3-element partition relatively simpler. Later, we need to do 5-element partition. Yeah. Because 3-element partition still has some problem, cannot give us a satisfied solution. Yeah. Cannot give us the solution in big theta of n. Not there yet. Very close, but not there yet. Okay? Then 5-element solution. Yeah. But that discussion, yeah, there is some good reason. So we go through this path. Yeah. All right, so let's start. Yeah, so in this problem, before we work on the implementation details, so let us do some preparation. Yeah. All right. Let us do this way. Yeah. Assume that the solution function is, remember, we use the recursive function. Yeah. So when you define a recursive function, yeah, so here we use this gen selection, so general selection. Yeah. Then 2 parameters. The first one, rank number k. Yeah. Second, input array, a array. Yeah. So 2 parameter variables. What do we return? Yeah. We also need to carefully arrange the return data type, because the return data we need to use for the next round recursion. Yeah. Problem size reduction, next round recursion, and so on. Yeah. So we still need to get all the data we need from this return data. Yeah. All right. Return an integer array, S array. We can return an array, right? Yeah. So function can return an array. Yeah. But what elements, what numbers do we store in this array? Yeah. So we store this. S of 0, we store the index of kth smallest. Index of the kth smallest in the original A array. Yeah. So we need it. We need to know that index. Yeah. All right. Yeah. So that's S0. Yeah. Index of the kth smallest. Right. This looks something, because you find an index, you solve it, right? Yeah. Kth smallest, you solve it. Yeah. Right. Yeah. Yeah, because we assume we solve it, right? Because this function, this is a recursive function. This recursive function, inside this function, we need to call the same function again and again. Yeah. But at the end, the solution, the answer stored here. Yeah. The first element. But we need to also store the remaining indices for those whose ranks less than k. In our recursive function call, we need that. We need that. Okay? Yeah. All right. With this careful preparation, then we go to the next step, analysis step. Now, So let's draw a diagram to get a good understanding of the problem. Our goal, find the partition element, the goal. All right, start from our experience. We need to use our old experience to help us, get some good arrangement of the elements. So what kind of old experience? Find the median of 3-element array. Find the median of 3-element array. In the insertion sort, when I give you example, remember at the end part, I give you two videos talk about sorting for small problem sizes. The first one, n equals 3. In that one, we use 3 comparisons to get arrays sorted. All right. Here, the median, find the median of 3-element array. We also need to use 3 comparisons. If you use 2 comparisons, you may not be able to find the median of that array for the worst case. For the best case, you can, but for the worst case, you cannot. Here, we have to cover the worst case, the bottleneck. We have to cover it. So we need to use 3 comparisons. Actually, we get that array sorted, 3 comparisons. Then we pick the one in the middle. Okay? So here you can see when n equals 3, sorting and find the median, you use the same number of comparisons for the worst case. Yeah. All right. Yeah. After that, so why we need to find the median of 3? Yeah. So this is our experience. Now we use this result. We will arrange the elements in a well-organized way to finally get that partition element. That's the reason. All right. All right, so question. Can we use, to eliminate some elements, use this result? But you need to do a lot of work. The answer is yes, but the amount of work, not trivial, pretty complicated. You need to do a lot. Yeah. Here, so let's work on it. All right. Choose the most convenient end first. So this method, you can see we use this method many times. Choose the most convenient end first. Okay, yeah. For example, in that binary count binary bits question, we use this way, right? Yeah, binary bits, we use this way, yeah. And another one, we use this. Fake coin problem. Remember, fake coin problem. N equals power of 3. We also use this idea. So here, we use another time. What is the most convenient n? Yeah. Because we need to find the median for 3 elements. So we need to group the given array in 3-element groups. Each group has 3 elements. And we will try to put all the elements in different 3-element groups. In that way, most convenient n is multiple of 3, 3r. Most convenient. Yeah. If not multiple of 3, we can easily handle it. After we solve this problem, if there is some remainder, we can easily handle it. Yeah, so don't worry. Just a little more tweaking, we can get it solved. Yeah, so we don't worry about that part. Yeah. All right. Now, for each element group, can we sort it? Yeah, here, this, greater than sign, so we get it sorted, increasing order from top to bottom. Yeah, increasing order. Yeah. So for all the groups, we get it sorted. We can do that, right? Yeah. And each group, we need to use 3 comparisons. Okay. When we get it sorted, at the same time, we know the median, right? Yeah. This middle row contains all the medians for these groups. Yeah. These R groups, for the R groups. Yeah, 3 R groups. Yeah. All right, so next. These are medians. We try to find one of the element in these R medians to be our partition element. To be our partition element. That's the trick. The trick is here. Or in other words, we use the median of the median. The median of these R medians. That's the idea. That's the key. Okay? The key. Median of all these medians. In order to do that, we choose R, an odd number, because in that way, the median is right in the middle. Very convenient. Convenient. Yeah. So we can assume that. Yeah. All right. Then we know n equals 6s plus 3. Now, in our calculation, so we will use new expression. Next, our goal, we need to find a partition element. Yeah, so that's the goal. Partition element somewhere in the middle. What element somewhere in the middle? The median of the medians. The median of those group medians. The median of the group medians. That's the key of the technique. All right, so with this idea, next we need to implement it. Implementation. Yeah. So here, let me describe the implementation details. Yeah. All right. Here, I use M star to represent the median of the group medians. Yeah. All right. Partition element. Yeah. Somewhere in the middle, we need to figure out what are those elements located at the left-hand side of M star, left-hand side based on their ranks. You know the meaning of ranks, based on the values of their ranks. What are those elements at the right-hand side of M star based on the numbers of their ranks? We need to know that. If we know that information, we can complete the partition step. Yeah. All right. First, all right, we need to find, yeah. So look at this step. Yeah. Those elements that are guaranteed to be less than M star. Can you draw in the diagram that will be guaranteed less than M star? Yeah. Here, these group medians, I just imagine we arrange in increasing order. How about that? Not in, yeah, so here I should not say, yeah. So here, there is a special, yeah, subtle part, yeah. Not because we cannot arrange, because we cannot sort it. Yeah. Here, I got some common mistake. Yeah, All right. Here, we cannot arrange the elements in increasing order. We cannot. But we can arrange in this way. All the elements at the left-hand side of M star, they have smaller ranks than M star, than that of M star. Why? Because remember the recursive function we return the indices of those elements with smaller rank numbers. That's the reason. Okay? Then the remaining elements with ranks greater than M star, automatically we put at the right-hand side. Yeah. But we do not sort it. Okay? We get that information, we do not sort it. Yeah. All right. So that's important. That step is important. Oh, with that assumption, now we need to mark those elements that are guaranteed to be less than M star. Here, I draw that circle around those elements. Look at these elements. Yeah. Look at these elements. Can you see they all have smaller rank numbers than M star? This is M star. Yeah, M star. Okay. Yeah, this one easy, strictly less than M star, right? So here we assume all the elements are distinct, still for convenience. Okay. So then, for example, this one less than that, but this one less than M star. So by transitive property, so you can see all these elements have smaller values than M star. All right. Similarly, yeah, here you can see there are 2s plus 1 elements in that group. Yeah. Step 2, those elements that are guaranteed to be greater than M star. Yeah. We can circle them in a similar way. These elements satisfy that condition. So you can see that easily. Still, 2s plus 1 elements. Okay? Then the remaining elements. We do not count M star. Then the remaining elements that could be greater or less than M star, we don't know. So we will find that part out later. Yeah. But we know there are 2s, those elements. S here, S here. Adding together 2s elements. Okay. All right. So then, next, we're very close to determine the rank of M star, but we need to resolve the elements for the step 3. 2s elements derived from step 3. Yeah, so the last thing, after we fix that, we can get the rank of M star. Okay? Yeah. But this part, we need to use comparisons. This to get that part clearly, we need to use comparisons. Actually, 2s comparisons. So each element, we compare it with M star, okay? Yeah. Because after those 2s comparisons, we know what are those elements less than M star, what are those elements greater than M star, right? Yeah. Also very simple. Yeah. So we move to the next slide. This time, we are ready to do the partition. With that information, now we are ready to do the partition. So let me draw this diagram. Because after we determine the partition element M star, if we know its rank, we need to get its rank number. After we get that rank number, it is in place. So this element is in place for sure. Partition element must be in place. Otherwise, how can you use it as a partition element, right? Yeah, you have to use some element that is in place to do the partition for this situation, for our purpose. Yeah. All right. Then we arrange known elements. The elements that we know their relationship with respect to m star. So less than, greater than. So we do the arrangements. Yeah. Step 1 elements. 2s plus 1, we know we need to arrange at the left-hand side of m star. Similarly, step 2 elements. 2s plus 1, we arrange at the right-hand side of m star. Remaining 2s elements, after we do 2s comparisons, we pay that cost. 2s comparison, that cost we pay. Okay, yeah. So then we assume little a number of elements, little a from 2s at the left-hand side of m star, and the little b elements sit at the right-hand side of m star. Yeah. And a between 0 and 2s, b between 0 and 2s, and a plus b equals 2s. How about that? Right? Yeah. So think about after this step, we get a partition. Okay? We get m star in place. And we get the rank number of m star. What is the rank number of m star? Yeah, you can see how many elements at its left-hand side. 2s plus 1 plus a, and itself has a position, so plus 1. So we can write 2s plus a plus 2. How about that? That is the rank number of m star. Okay? With this information, then we are ready to drop one of the two subarrays. Left subarray or right subarray, this time we need to use the k value to help us determine which subarray should be dropped. Yeah. So we will get that part in the next slide. All right, so let us do the elimination part. So this is the elimination part. How to drop a subarray based on 3 cases. Yeah. The first case, the simplest case, after the partition, case 1, when k equals 2s plus a plus 2, the rank number of m star, right? So rank of m star. Then we find the location of the element. Yeah. So solution. So return the index of m star. That's the solution. Yeah. The easiest. Case 2, this time k less than the rank number of m star. That means the kth smallest element sits at the left subarray. So we should drop the right subarray. And we should do recursion on the left subarray. Okay? So then we call recursive function. Same function, but this time we change the data part. The data part, we choose the original array, but we use the rank number. Yeah, here, yeah, because here I use the rank number starting from 1, not 0. Yeah, so the rank number minus 1 equals the index number. Okay, yeah. So when you manipulate the data, you need to use this relationship. Okay, yeah. So here we use the rank number here. Okay, yeah. All right, yeah. All right. Rank number can be converted to the index number. Okay, yeah. So you can find those elements in this array. Yeah. So you call returns. Yeah. Third case, when k greater than the rank number of m star, this time we should draw the left subarray and do recursion on the right subarray. Yeah. All right. So that's like this. But this time, when you do that, you need to modify the rank number. We drop the left subarray, including m star. We also drop the m star because it's not a case 1. So m star can be dropped. When you drop m star, so we drop the, we reduce the rank number k by 2s plus a plus 2. So all these elements eliminated. So eliminated. Yeah. After elimination, we update the rank number. New rank number. Okay. Yeah. Then the corresponding data, we apply the recursive function call. Yeah. So you get a, whole recursion step resolved. Yeah. So we complete partition, we complete recursive function. Yeah. So we finish this video. In the next video, we need to do efficiency analysis. Is this way can give us, if this way can give us the solution in big theta of n. Big theta of n. Yeah. All right, so let me finish